Okay, we're ready to apply Pascal's principle. So here's what's happening. You're given a hydraulic lift, and the piston areas are the piston radii are 5 centimeters and 20 centimeters. So on one side you have a 5 centimeter radii, on the other side you have a 20 centimeter radii. So this is 5 centimeters, this is 20 centimeters. Okay, and it says what is the maximum load that can be lifted if you exert a force of 150 at the input piston. Now, you have to understand here that the input piston is always the piston with the smaller radii. So that is why we are exerting a force of 150 newtons on this side. I'm going to ask how much are we going to get out of the other side. Okay, so this is our input piston, this is our the other piston. So we're going to figure out how much load it can carry. So there's some load it can carry. We're going to figure out the maximum load that it can carry. We can find the weight, and then we can find the mass. We can do whatever we need. Okay, so we're going to apply Pascal's principle to this. It's very simple calculation. So what we'll do is, we know that the pressures are equal. We know P1 is equal to P2, and if P1 is equal, then we know that F1 over A1 is equal to F2 over A2. Great. Okay. So now let's plug in all our numbers. F1 is 150 newtons, and we'll divide it by the area on the left hand side. It's pi times r square. Now the 5 centimeters, we need to convert it to meters. Divide by 100, so it gives us 0.05 square. And on the other side we have F2, and we're going to divide it by pi times 0.2 square. Okay, great. So the pi's cancel out. Okay, before you plug in the numbers into your calculators, always try to simplify. In fact, this problem can be solved without putting anything into the calculator. You'll see this. Okay, so F2 is 150 multiplied by 0.2 square, and then you divide it by 0.05 square. Okay, now if you look at this carefully, you see that the 0.2 over 0.05, okay, I can just put them all into one parentheses and square. Okay, 0.2 is 4 times 0.05. Okay, so what I have is 150 times 4 square. Okay, and so now we have 150 multiplied by 16 as our answer. Okay, so you don't need the calculator for this. To do 150 times 16, that's a simple. Okay, so it is nothing but 2400 newtons. So it's 2400 newtons is what we can get out on the other side. Okay, so simple, quick calculation. And also, if you want to find the mass, you can divide this by 9.8 to figure out the mass. I would like to also discuss one more thing in this video, which is namely the fact that in all these hydraulic press applications, one must be very careful in understanding that yes, that you can get a large amount of force, okay, by exerting a small amount of force on one side. However, please do not confuse yourself into thinking that I can get a large amount of energy on one side by exerting a small amount of energy, because that would be violation of the principle of energy, which is energy cannot be created or destroyed. Okay, and also the whole concept of perpetual motion machines and all those things, those things cannot be possible, and I don't want you to think that that's what's happening here. Okay, so let's do a quick calculation and show that the work done is the same on either side of a hydraulic jack. Okay, that never ever violates that. So what we'll do is we want to show that the work done, okay, on one side is equal to the work done on the other side. Okay, that W1, okay, and that W2, the two works that we get are the same. Okay, so what we know is that we're going to use first our definition, that the work done is equal to nothing but F1 times delta X1. So this is the work done on the left hand side, and on the right hand side it will be equal to the work done, okay, by the force F2. So it will be F2 times delta X2. Okay, now we know that the two pressures are equal. Okay, so what we can do is I'm just going to call the pressure P, and now I know that F1 is nothing but P, oops, not P1, but it is equal to P times some A1 times delta X1. Okay, where A1 is the area to the left hand side, and similarly the force on the work done by the other side is equal to P times the area on the other side multiplied by delta X2. Great. So we have our two works. Now, if you look at this expression, what we know is that A1 times delta X1 is nothing but the volume on one side, and this A2 times delta X2 is the volume on the other side, the volume change. Okay, so whatever volume that is compressed on one side, that's the volume that goes up on the other side. Okay, and we understand that these two volumes absolutely have to be the same, because you're not pumping any fluid into this. So these two volumes are equal. So delta V1 we know is equal to delta V2, and consequently we know that W1 is equal to W2. So the work done on one side is equal to the work done on the other side. So we cannot, okay, please understand, we cannot get more energy on one side compared with the energy that we put into one side, because that would solve all our energy crises, obviously violating the principle of energy conservation that states that energy cannot be created or destroyed. It can only go from one form to another. Okay, so that's for some Pascal principle application.